Ladies and gentlemen, please help me welcome Associate Professor Tan Tin Wee.
Thank you very much for the wonderful introduction. My name is Tan Tin Wee, and I'm from Singapore. And I just flew in and woke up at 4 a.m. this morning and came here by plane. It was very nice to see Putrajaya and Cyberjaya, so modern and wonderful, crossing by the bridge over to the PICC. The view and the vista across the bridge as it's opened up was fantastic. And to come here to speak with all of you and share with you some of my ideas about research at the speed of thought. It's really wonderful for me to be able to be here to meet all of you, especially all my old friends, Kamal, Suresh, Suhaimi, Farida, and Tommy Chen, my former boss. He's somewhere at the back, I think. And we worked with each other for more than 20 years ago. I think before some of us students were born. And also another colleague from Australia. Where is he? Andrew Howard, right? Outside, okay. So, this is a very long history of interaction of how colleagues from all over the world come together and work together towards a common goal. And I'm really delighted to see many of you students here in the audience who have come together and worked on wonderful projects, learned from each other, created history, and gathered together and started this wonderful path of friendship and interaction that perhaps will last long after you have left this event, Futurescape MyRen 2016. I'm currently the director of the National Supercomputing Center, NSCC. And over at the National Supercomputing Center, we've just taken ownership of a 1 petaflop supercomputer. That 1 petaflop is, or you might want to Google it and find out what is 1 petaflop. And that's 1 quadrillion calculations every second. That supercomputer has 30,000 cores. This is the first time that Singapore has a 1 petaflop supercomputer in the petascale range. And that supercomputer is connected to a high-speed network, very much like your MyRen. It is connected to not only institutions in Singapore, but also to research institutes, universities, research networks throughout the world. So today, I would like very much to share with you our thoughts about how the future is shaping out to the point where we can carry out research at the speed of thought by combining high-performance computing, HPC. I don't think this laser pointer is... Okay, here, yeah. You can't see the pointer, right? It's okay. By combining HPC, networking, storage, input-output devices, visualization, and combining it with, you see that standy banner there? By combining with robotic, automated systems that operate within laboratories. So, that's quite a mouthful, but I will go through and explain to all of us here in the audience what I'm talking about. But first, let's cast our mind backwards in time. In 1993, that's a long time ago in the previous millennium, I was a biochemist in the Department of Biochemistry. And I was trying to do research, but I was really lazy. I had to go search for research papers in the library and go through thick books and volumes and journals and struggled a lot to get information in order to help me carry out my research in the research laboratory. And then I discovered the internet because my good friend and my former boss, Tommy Chen, built the internet in Singapore. And I inherited that from him. And with the internet, I built Gopher sites, I built Wave sites, and I built the first worldwide website in Singapore containing biological information. And with that, it allowed me to understand the possibility of the future that is now today. 25 years ago, I envisioned the possibility that soon there will come a time when the biologists need not travel to the library to do research, to carry out literature survey. No need. Should be able to access a wide range of information resources by surfing the net through the computer at the tip of your fingers. At that time, there was no mobile device. The phone is just a phone. The mobile phone is like a brick. Yet, at that time, because of the internet, it showed me the way forward, the future. Today, none of us ever think twice about accessing information at the tip of our fingers. Whatever question you can think about, you ask Google. Is that not true? Whoever you want to ask a question, you WhatsApp the guy, or you connect the guy, or email the guy. The whole world is so interconnected. But remember, it was not so back then in the 90s. In 20 years, we have achieved what humanity has never achieved before. To be able to contact anybody in this world, in this globe, anytime, anywhere you want. This, arguably, will be one of the historic moments in the landscape of history of mankind. A few years back, I discussed the possibility 2 decades down the line. Is it possible for us as researchers, as scientists, who are at the forefront of technological advancement? All technology has to be done in the research lab before it can be promoted out in the open. And a lot of that research comes about from a lot of hard work. Can we speed it up with the use of robotic systems like Futurescape, like this robot that popped up from this dais a few moments ago? Not just only to do a dance, but also to do some work for us. Isn't that nice? To be able to get one robot, maybe 10 robots, to carry out the work for us at our control, possibly at the control of the tip of our fingertips, using mobile devices so that we can be even more productive and more efficient. In 2016, a few months ago, I decided in a moment of retirement from the Asia Pacific Bioinformatics Network to make a wild prediction. Just as 20 years ago, I made that crazy prediction that perhaps in the future, we will be able to access knowledge and information at the tip of our fingers, which today is true. Maybe today I will make a prediction into the future and guess what might it be like carrying out research 20 years from now. In 20 years, I may be no more. But every one of you in the audience, these young people who came on stage, you will be in the prime of your life. And mark my words, you will be at that another range of technological developments that is incredible to imagine today. But let me I invite you to join me on this imaginative journey to think about what would it be like in the future in the research lab where we invent new technologies and make new scientific discoveries never dreamt about before. And as a result of that technological discovery and scientific research, we are able to further transform the world into something which we have never imagined possible before. We will at that time create even more new jobs that have never been described before and invent new career paths that we have never ever dreamt of. So one of the predictions as a professor in the university in the molecular biology department, I thought maybe the time will come when at the tip of the biologist's fingers or the scientist's fingers, we will be able to design experiments. We will be able to execute these experiments robotically. We can send these experiments to an automated pipeline, and the results will automatically be gathered for computerized analysis. Is this really possible? In 2012, I was inducted into the Internet Hall of Fame for being a global connector. And you can see in the picture there, some people may recognize famous people like Professor Vinton Cerf, right in the middle. And of course, I was right at the far end, the right-hand corner, being the only lonely Asian person in this picture. In that Hall of Fame inaugural inductee session, I spoke about how the internet converged with biology research in order to create a new possibility of how the interweaving of the internet and biology will lead to the possibility of new discoveries in medicine. And today, as you may have recalled, President Obama, the outgoing President Obama, has announced the possibility of precision medicine. And that comes about from the possibilities resulting from the interconvergence of the internet with tremendous advances in genomic research, genome science, and in fact, for example, in Malaysia, there is a Malaysian Genome Institute, in case you didn't know. It is now possible for us to sequence everyone's genome in this room. Everyone, you can have your genome sequenced at a cost less than $1,000. There are many projects in every country that is sequencing the 10,000 genome, the 100,000 genome, the 1 million genome project. What does this mean? Once we collect that much of data, it's now possible to combine it with the internet, have that information readily accessible at the tip of the medical doctor's fingertips, right? This is far-reaching and unprecedented in the history of mankind. That the physician can have that possibility of accessing not just the information about your illness, but also the genome that is in your body. A few years ago, I managed, that was last year, was it? I gave a talk at TEDx Singapore 2015, last year. And I postulated the possibility beyond just the convergence of the internet with biology, the possibility of how the combination of biology, life sciences, medicine, combined with the internet, can now be further combined with industry. Now, when all these data becomes collected and stored in the data center, the amount of energy required to store all this information and to compute on them becomes ever so greater. Can you imagine all the genome data of your body all stored inside databases that need to be kept alive for the rest of your life, which will be 80 years, 90 years, 100 years, and that data needs to be accessible so that your doctor anytime can access the data. And your genome is more than the 3 megabytes of data that is contained in your DNA. It contains information about all the parts of the genome, what sort of diseases they cause if there is a mutation. So I ask the question, can we store that much data in all our data centers? Would these data centers be environmentally green, burning up all that electricity? Every time you save a video image, it gets stored in maybe some Google data center somewhere. You copy it to 10 persons, the same video recording will be multiplied by 10 times and stored somewhere else in somebody's directories, in some data center somewhere in the world, which will be backed up in 3, 5, 10 different locations, all but spinning disks, consuming electricity at far unprecedented rates. Is it possible for this to be sustainable without causing global climate change? So in this talk, I asked the question, is it possible for the future that I described of how the interweaving of data storage with the internet, with medicine, for example, can combine together and cause global warming because of using up so much electricity? So in this talk, if you were to look at this video on YouTube, I speculated on the possibility that maybe the next computer that I will build, the next supercomputer that I build, might be built with something called industrial symbiosis. How the output of an energy generating system, an industrial system that is generating waste heat, can now be usefully made into something as the input of another system. And by combining these two systems, we may make the combined system more energy efficient. Is this possible? Supercomputers use up a lot of electricity. The supercomputer that I built, which I will show you in a short while, uses up something like 1 megawatt of electricity for 1 petaflops. If the amount of energy generated, the amount of energy used by the CPUs is run through a semiconductor. And everybody knows a semiconductor is the poor conductor of electricity, right? Primary school physics. Because it's a poor conductor of electricity, it generates heat. And that heat has to be gotten rid of by cooling the system down. If you have a data center that is storing so much data from your genome perhaps, from your video clips, whatever, and you have to cool it, you will spend double the amount of electricity just to spin the disk, just to compute and run through the CPU, and then you have to have refrigeration system, air conditioning system to cool the heat generated by the data center. Can we make this more efficient? Can that heat generated be used somewhere else? Then some people suggested maybe we should build data centers storing all this data connected by the internet in Iceland, because Iceland is very cold, right? You make use of the cold to cool down the heat that is being generated by the supercomputer. And there will be lots and lots of supercomputers throughout the world in data centers all over the world. Maybe we should put all our data centers in Iceland. Would it help? But how about me in Singapore? It's so hot today. Can we do something about it? So it turns out that my engineering mentor told me, Singapore has its Iceland. Huh? I said, where is Iceland in Singapore? We are both island, yeah? But Iceland is a lot of ice somewhere far north of where Santa Claus comes. How is it possible that Iceland is in Singapore? So he pointed to an island called Jurong Island in Singapore, south of Singapore, and he says, that is our Iceland. So I went there to take a look, and lo and behold, that was where the liquefied natural gas industry was being set up. And liquefied natural gas is minus 162 degrees centigrade, cold. I said one day maybe I will build my data center next to it and take the minus 162 degree cold energy and cool my data center. So to cut a long story short, we are now trying to work towards the possibility of converging both the internet, biology, medicine, together with industrial systems like a liquefied natural gas receiving terminal with lots of coal, and combining these together to form a green, environmentally sustainable supercomputing data center that is processing and computing genomic analysis as one possible applications amongst others. So now I said, wow, if I can combine all this together, can I combine even more things together? So I was surfing the web, and suddenly I realized, because I'm a biologist and very lazy one, can I do experiments and have that automated? And I found this website, Emerald Cloud Lab, is able to do cloud research experiments. Now there's a lot of talk, and there's some companies out there behind you talking about cloud computing. You don't have to buy a computer and have the computer in front of you before you can do some computing. It can be somewhere in the cloud, in a data center somewhere. So I asked the question, is it possible for me to carry out a research lab experiments somewhere out there? I don't even have to do the experiment myself. Somebody will do it, or some robot will do it. Or maybe this robot here inside here will do the experiments for me. All I have to do is use my fingertips, use my brain, design the experiment, and click a few buttons, and I can design, I can execute, I can explore the data, and I can analyze the data all in one go. And if I can combine a green, sustainable data center supercomputer, combine it with advanced networks like MyRAN, SingleRAN, and other networks like Tien, combine that with automated research laboratories with robots working behind it. Wow, could this be the future 20 years from now, that we can do even more fantastic things with the infrastructure that we are building today? The same infrastructure that you have been experimenting on in the last few days. This means that if we can construct something like this, combine this company, Emerald Cloud Lab, we can actually access state-of-the-art laboratories without ever leaving your desk. You can dream of the experiment and conduct these experiments, test your hypothesis online, and then have that data analyzed and computed. You can order your experiments, any one of these experiments, and somebody will do it for you. And these are the ones available today. In other words, today you can do it. Is it possible for us to combine all these things together? What's coming up next? The armchair biologist? Is this possible? So I went to my old friend in Novartis, Singapore, and Dr. Thierry Diagana. He's carrying out research in malaria, finding out cures for malaria. So I asked him, what do? You seem to have a lot of robots inside your research lab. What do you do with it? So he showed me some pictures, and here you are. Amazingly, his company in Novartis, Singapore, is already a major user of robots. You see this gentleman there in the middle? The technician there is in control of robots marked in, painted in bright orange yellow. You see one robot in front, but you see in the background there are several other robots. There's something like 10 different robots with robotic arms carrying out pipettes and pumping liquids and test tubes and so on. Wow, that's already here today. But are they all connected or not? That was my question. It is now then possible to do this. So isn't it amazing that the future of research could well become a reality today as we slowly embark on weaving together the internet, networks such as MyRAN, combining it and interconnecting it with other research networks in other places in the world, combine that with the research area that you're interested in my case, biology and precision medicine, combine that with green data center technologies to make it sustainably green, and combine that with robots and automation such that we can carry out research at the speed of thought. What steps can we carry out to make this futuristic prediction a reality today? So in Singapore, I was transferred from the internet and transferred out from biology, and now transferred to run the National Supercomputing Center of Singapore to build a 1 petaflop supercomputer so that we can support high-performance science and engineering, and to support academia, to support researchers and industry. This petascale supercomputer is interconnected with each other at a super high speed. This is a multi-gigabit per second network that is interconnecting the universities in Singapore as well as the research agencies. ASPAR is the Agency for Science, Technology and Research in Singapore, which runs something like 20 research institutes in all areas: material science, chemical engineering, all the way to the life science, biotechnology, and including IT and high-performance computing, all wrapped up into A-STAR. We have 30,000 students in Nanyang Technological University and 35,000 students in National University of Singapore, as well as the MIT-supported SUTD. And they're all interconnected to able to submit jobs over InfiniBand interconnections right into our supercomputer. Now, this supercomputer is not new. We had a number of failures before, but we came back again to persevere, to try to see how we can overcome all these setbacks in the past. And now we are building this National Supercomputing Center 2050, launched this year 2016, in order to promote this possibility of supplying supercomputing power to boost the research collaboration and to boost the networks, high performance advanced networks that are already being implemented by MyRAN. We managed to hit the top 93, but as of November this year, that is last week, we dropped to 115 from 93. This is to illustrate to you that the developments in this field is moving so rapidly. Before you know it, what I just predicted to you may well have already happened. It means that the jobs, the schools that you're studying in, the work that you're involved in may be superseded by jobs that have never been dreamt of, that have not yet been invented. This means that each and every one of us should be thinking about what is tomorrow's job that will appear and how we can be prepared for that future. So this supercomputer, and I invite you, if you are interested to visit, come take a look at it. It's to fulfill the purpose of democratizing access to supercomputers. Most supercomputers are accessible only by the elite, the rocket scientist, the professor who is the boss. Only he or she can access a supercomputer. But here in Singapore, we are trying to do the opposite, to make the supercomputer accessible to ordinary people like us, not rocket scientists, but ordinary people, so that by putting that supercomputing power in your hands, you can dream of not just supporting our national research initiatives to attract industry, industrial research collaboration, but also to enhance our research capabilities in Singapore or in your respective countries that you come from. By democratizing access to supercomputers, we hope that talented people like each and every one of you in this audience can have a chance to see how they can improve, invent the future as it comes. We are based at the level 17, and in Singapore we are very small, so everything has to be built up, and it's arguably one of the highest supercomputers in the world. The data center looks like this: 14 racks of storage, as well as nearly 20 racks of high-performance computers. There are about 30,000 cores in this supercomputer, cooled by 3 different cooling systems: air conditioning system, chilled water, as well as hot water cooling. Have you heard about it? The computer is running hot at 40 degrees, and by the time the hot water goes in, it becomes 45, and then we vent it out in at level 17 where the wind is pretty strong. Hot water cooling, another green and environmentally more friendly system for cooling data centers. And we also employ direct-to-chip cooling. And the network operations monitor 6,000 different sensors to adjust the temperature, the fluid flow, the heat, the humidity, the temperature, etc., all controlled by an integrated data center information management system. Hardware is as shown. We have 13 petabytes of storage, all the CPUs of 30,000 cores, over 1,000 over nodes, are interconnected by a 100 gigabit per second high-speed EDR interconnect with NVIDIA GPU nodes as well, and visualization nodes. This is a huge range of software is being installed on this system. It is a CentOS Linux operating system, which makes it easy for people to use. We make use of high-speed InfiniBand to interconnect our research groups for high-performance data transfers, and we are building a national InfiniBand interconnect system that will allow us to have our users directly connect using a federated identity management system for all our stakeholders to easily log in 5 steps using their passwords from their own institutions without having to ask us to fill up forms. This national InfiniBand infrastructure will be expanded to include hospital sites, Rolls-Royce Aerospace Park, or even to Keppel Shipyard, where they build large oil rigs and design structures for using supercomputers for large oil rigs that are shipped to deep sea oil drilling systems. Beyond that, we have already interconnected with US with a 100 gigabit per second link and a 10 gigabit per second link to Europe. And soon we will be negotiating for a 100G link to Japan. This creates that InfiniBand data bus that allows us, our researchers, to access supercomputers, research lab with robotic systems in these developed countries, in Europe, in America, and in Japan, that already have strong robotization and robotic laboratories already implemented, such that our users can not only compute, we can also access the data immediately and directly from these advanced laboratories by tapping on these high-speed networks that we are building through the Singapore Research Education Network. Just like what MyRAN is, the Malaysian Research Education Network, if you plug into these advanced countries, there is an immediate possibility for you to access these resources. Internally, we are within the country, within Asia, we are also members of TN. And what's interesting is we are starting already to connect our research lab at the Genome Institute of Singapore, GIS. Their research lab has an X10 DNA sequencing farm, and they produce terabytes of data per day. All that data across 2 kilometers distance dark fiber, we are able to pump that data and write into our parallel file system in our supercomputer in the 17th story. And then have that computed and analyzed with high throughput and send the data back to their storage for their researchers and genome scientists to analyze the data and make new discoveries as a result. We have a 500 gigabit per second link between these two sites separated by 2 kilometers in 2 campuses, Biopolis and Fusionopolis campuses, connected by a dark fiber. We are running 500G across these 2 connections. Globally, we have already piloted the possibility of connecting InfiniBand around the world. In 2015, we built the world's largest, longest spanning InfiniBand network in a ring around the world in collaboration with our European and American partners. So we thought, well, if everybody is in one singular subnet, only one person can control the whole system. How about if we have federated and everyone control their subnets of supercomputers, and somehow we route their traffic. InfiniBand does not yet support routing, but TCP/IP Internet Protocol does. Can we combine the two again? And then we decided to set up the InfiniBand routing across 7 subnets over 4 continents. Not being satisfied, we are Singaporean, always not satisfied. So we decided to ask, is it possible for us to build cloud computing, run it over HPC, run it over InfiniBand connections, bypassing the kernel, jump over and bypassing the TCP/IP stack, and directly connect to the network interface for a low latency interconnects between cloud instances. And lo and behold, it was possible. We were able to successfully build InfiniCloud. InfiniBand supported cloud instances across 4 different countries in each continent listed here. This shows us that if we create a fast enough data bus between research labs, between countries, between students, between professors, between researchers, with industries, we can build a global fabric that will allow us to carry out research 2.0, research 3.0, research 4.0, maybe. Is this possible? Andrew Howard, who is seated there, please stand, Andrew, was the man who supplied this chart. He was able to transfer 1 terabyte of data in 24 minutes from Singapore to Canberra and back. This allowed him to carry out a lot of research experiments at a super high speed. We are now thinking, and I think, have you demonstrated it yet, the DTN, the data transfer node, to build, not yet, soon, a data wormhole between Singapore and that spot there called the NCMIR, which is an cryo-electron microscopy research lab. Wow, I can't even pronounce it. A research lab that automatically gathers electron micrographs, and they have many machines there. Can we control that remotely and have that robotized as well? We are working on it right now. By creating a wormhole such that the data popping in on one end can pop up at the other end, where distance disappears. So in the process of doing this, we have learned a number of things, and Mark Ellisman is the director of that institute, and we hope by connecting with the San Diego Supercomputing Center and the University of California University of San Diego Image Database, NCMIR, we can then start to pilot the possibility of a future of biology or biological research that is data intensive and data driven, to combine that with Industry 4.0, where the fourth industrial revolution involves the combination of cyber physical systems, cyber internet, physical research laboratory equipment, robotic experimental systems. Combine the two to create maybe Science 2.0, Research 3.0, and so on, to allow us to search, retrieve, interrogate, simulate, model, machine learning, artificial intelligence, deep learning. Combine all these together by building this infrastructure to support high performance computing, high throughput computing, high performance data analytics, high performance data transfer using this InfiniBand infrastructure, incredible visualization power, and integrate all that, number 1 to 5, integrate all that with robotic, automated labs in an artificial intelligently manner. We have seen industry go from 1.0 to 4.0. Within my lifetimes, for sure, I have seen Industry 3.0 become Industry 4.0. I was born at the time when Singapore was part of the Malay Federation, and when you sang Negaraku, I vaguely recall when I was a kid, I was a Malaysian as well. And we have seen tremendous change. These revolutions will continue. 3.0, 4.0, 5.0. I now like to invite you to share with me in that wild prediction that the future of research, the future of scientific endeavor will be automated. Join me as we enter the future of biological research, research at the speed of thought, because the infrastructure that we build today by students, by researchers, by professors, by engineers today will build the framework for us to support science research 2.0, 3.0, 4.0, and beyond. And by making research discoveries move at the speed of thought, we will create new technological advances that will really change the shape of humanity and hopefully avoid the disasters that we have gone through, and hopefully in a green and sustainable manner that will result in the advancement of mankind to invent new jobs, new professions, new careers, new and exciting, wonderful vistas that will open before us. Join me for the research at the speed of thought. Thank you very much. And may I invite you in March next year to come to our Supercomputing Frontiers Conference, sales pitch, a word from our sponsors, and join us at this conference where we will discuss some of these thoughts further. Thank you very much. If there are no questions, I will hand over to the next speaker.
Thank you very much, Associate Professor. Now we will open the floor to the audience if you have any question to ask. There's Mike at the center, can ask questions. Please take this chance because he's flying to Singapore right after this.
Thank you very much. Question, yes. Come on.
I think one of the major challenges in terms of providing that infrastructure to the group of researchers is actually to prepare not only the hardware infrastructure and also the human side of it. And if you can share the challenges faced by your organization in terms of providing the service platforms as well as the talents to support the multidiscipline research in terms of developing research content in your country, that would be good.
Yeah. May I answer your question this way? We are making efforts to train people for the future, to future-proof our students. When I was young at 12, I took the primary 6 exams. I don't know what you call it here. Right? In Singapore, we call it the PSLE. My dad told me after the exams in December, my son, if you fail your primary 6 exam, where will you get a job? I will send you to the typing school to learn how to type. At least, if you know how to type, Pitman typing school, then maybe if you fail your exam, you at least get a job as a typist. I said, yes, Papa. I go to the Rex Cinema near Little India and went for the Pitman typing course to learn how to type. In case I fail my PSLE exams, I need to get a job as a typist. Is there such a job today? There is no such job as a typist. Not because there is no such thing as typing. Now you have finger swipes, right? But you still need to do the keyboard too. But I was future-proof because now I can type very fast. I can write computer code very fast without looking at the keys. So this is one example of how a job has disappeared. But new things can derive from that skill. If we can find things that we can train our students in that will future-proof them 20 years from now, such that even though jobs like typing disappeared already, they will have an advantage by learning how to type fast. Because they can write computer program faster than the other guy has to use one finger typing, So this is an example of how today we will have to look at ways in which we can inspire, we can share our visions, just like what I'm doing here. This is exactly what I'm doing here, trying to share my thoughts and visions and inspire young people in the audience, talented young people, so that I can get out of your way and let you bring in the future that I can never imagine of. But it's already a seed planted in the minds of each and every one of you, that the possibilities going forward are tremendous. It is up to you to imagine, and up to you to increase your level of curiosity, and up to you to create new ambitions by combining your talent with your ambition, with your vision, and weave them all together and bring in the possibilities that have never been dreamt before, which I cannot predict for you. I can also only make crazy predictions like this about research at the speed of thought, just to stimulate your ideas, inspire you to invent something for yourself. By sharing with each other ideas, reduce the barriers of interaction, talk with each other such that new ideas can come out. And then work hard to study, Don't forget that too. Thank you.
Thank you very much, ladies and gentlemen. Associate Professor Tan Tin Wee.
Thank you very much.
And with that, we would like to invite Professor Dr. Suresh Warren to present a token of appreciation to Professor Tan Tin Wee.
Professor Tinvi is an old friend of mine, so it's a great honor to give him this gift. It's also very nice that he came down all the way from Singapore to give us this talk. Let's give him a big hand.
Safe flight home, Professor Tin.